Welcome you all for this yet another lesson on aircraft performance. I find that this aircraft performance lessons are being well received from several people, and I find that people are benefiting. So it encourages me a lot to include more lessons. So this is in continuation with the previous lesson where we talked about Enroute provisions. Now we will see some more aspects of Enroute performance requirements. Let's quickly recap what we learned in our previous lesson. We saw different definitions, and we saw the concept of gross drift down altitude and the net uh, drift down altitude and the net flight path. And we also saw that there is a net flight path must be positive at least 1000 feet above all terrain and obstructions all along the route. That was a 1000 feet rule which we saw. We also saw a 2000 feet rule where the net flight path must permit the aeroplane to continue flight from cruising altitude to an aerodrome where landing can be made, clearing vertically by at least 2000 feet all terrain and obstructions. And I try to elaborate the difference between these two rules, and I will take another 30 seconds to recall. In the 1000 feet rule, the entire route and the worst case scenario is taken, and at any point, the net flight path must clear any obstruction by 1000 feet. So it's a stiff rule because at some places where the obstruction has already been passed, maybe you are not able to clear. So that's why the requirement of the 2000 feet uh, came in. And in this, if there is a very small segment where the 2000 feet rule cannot be met, a small detour in the route which can be planned, and as long as the regulatory authorities are satisfied, then they would accept a small deviation in the route and getting back to the route once the particular obstruction is cleared. So that's what is the difference between the 1000 and 2000 feet rule. Let us get on to this lesson. The rule position regarding minimum flight altitude. The rule says that an operator shall establish minimum flight altitudes and the methods to determine those altitudes for all route segments to be flown. And every method of establishing the minimum flight altitudes must be approved by the authority. That means all these procedures and to determine the minimum en route, etc., will be uh, uh, listed listed in the operations manual of the operator, and those would have been approved by the respective regulatory authority. That's what this rule means. Before going on to how to calculate minimum flight altitude, let's understand that there are several other requirements as required by the regulatory authorities to fulfill several other clearance requirements. I'll just briefly touch upon them. I'm sure you are all aware of uh, all these provisions, but we are going to consolidate all these requirements into one, and that's why I want to recall them. One is the minimum obstacle clearance altitude and the minimum off-road altitude. They correspond to the maximum terrain or obstacle elevation plus 1000 feet for elevations up to 5000 feet or up to 6000, and 2000 feet elevation exceeding 5000 or 6000. This 6000 is for FAR, so let's not mix up this. Let us understand 1000 feet elevation up to and including 5000 feet, and 2000 feet for elevations exceeding 5,000 feet rounded off to the next 100 feet. So that's the requirement for of the minimum obstacle clearance and minimum off-route altitude. Or legal requirements or provisions. Two more, the minimum safe en route altitude and the minimum safe grid altitude. They correspond to a maximum terrain or obstacle elevation plus 1500 feet of elevation up to and including 5000 feet and 2000 feet for elevation above 5000 feet and below 10,000 feet, and 10% of the elevation plus 1000 feet above 10,000 feet. So these are the requirements, legal requirements to be fulfilled for the minimum safe en route altitude and minimum safe grid altitude. Having gone through these different legal requirements, now let us sum it. Of course, it's cumbersome to keep calculating each and every altitude and try to satisfy the legal requirements. So we consolidate all these requirements and we arrive at this for calculating the minimum flight altitude. So we set it up as above 10,000 feet. It is considered acceptable to carry out uh, obstacle studies and fix up a minimum flight altitude which is equal to the highest obstacle elevation plus 2000 feet. So this is considered as acceptable by the by almost all legal authorities when planning the en route segment. Previous lesson of en route performance, we generally talked more about an engine failure scenario, one engine failure scenario, and the requirements thereof, and for obstacle clearances, etc. But let's not forget that there could be other failure situations which force the situation to carry out a diversion or to carry out a descent if such failures happen. One of them, and one of the very critical failures that could happen is the pressurization failure. There could be rapid decompression failure, and which will lead to rapid drop in pressure, and of course which will lead to lack of oxygen. That means the normally when we fly the aircraft uh, internally it is pressurized to very high levels to keep the cabin altitude at much lower levels at around 8,000 feet, so that the passengers are at great comfort, or at least that's the legal requirement. But should there be an emergent situation in which the aircraft loses the pressurization system, the pressure inside the cabin is going to be equal to the outside pressure, and there is going to be lack of oxygen at very high altitudes. So we need to understand and learn the provisions of such emergent situations, which also have been specified in the rules. Before getting on to the actual lesson, let's go over the systems. There normally are two types of oxygen systems that are fitted in the aircraft. Why we are discussing this? Because it is going to affect the calculations of timings and the altitude, the time the aircraft can descend and maintain at different altitudes. All these are going to be affected by the different types of oxygen system. So as I told you, there are two types of oxygen systems. First is the chemical generator system and the gaseous system. So there are rules and regulations which govern the oxygen requirement for crew and passengers as well. So, in fact, the requirements of the crew are much more stringent, obviously. So, as long as the passengers' provisions are met, it is assumed that the crew provisions will also be met, because the normally the provisions for oxygen requirement for the crew are uh, much higher levels are catered for by the aircraft manufacturers. Therefore, we are going to see this in greater detail. Uh, Talking about the chemical generate oxygen systems, the salient features are, once we all know that once there is a rapid decompression, the oxygen mask from the cabin drop automatically, and the passengers have been advised to start using the oxygen mask as soon as it happens. Once the oxygen flow starts, then there is no stopping in the system. The oxygen continues to flow, which only means that there is no control. Thereafter, you can't stop whether you want it or no. And the quantity and pressure is independent of the altitude of the cabin or the aircraft. And depending on the system, the supply is for a specific period of time, it is specified. For example, for some aircraft, it is for 15 minutes or 22 minutes of supply is possible with aircraft full load or full passengers. So that's what is the salient feature of the chemical generator oxygen systems, which means the limitations of such a system is going to be much more stringent. Therefore, we are going to learn about this in little bit greater detail. As against the chemical system, let's go through the salient aspects of gaseous system. The configuration of the gaseous system is customizable. That means depending on the aircraft type and operator or the routes which it follows, you can configure the oxygen number of cylinders, the pressure, etc. The quantity and pressure is of the oxygen used is dependent on the altitude of the aircraft. So if the aircraft has come down to a lower altitude, that much more oxygen is preserved, and therefore your time supply time uh, uh, increases a little bit. So this, therefore, we can conclude saying that the supply time of oxygen depends on the flight profile planned of the aircraft, and of course, the supply stops below 10,000 feet, conserving all the oxygen. See some legal and rule positions regarding the supply time requirements and thereof. So here the table gives the flight altitude and different altitudes, and as to what should be the provisions. For example, above 15,000 feet, there must be supply to all 100% of passengers for the entire duration. And greater than 14,000 feet and less than 15,000 feet, it should supply to 30% of the passengers. And above 10,000 and less than or equal to 14,000, supply to 10% of the passengers, not required during the first 30 minutes. And above 8,000 and less than 10,000, supply to two passengers. This is because all passengers are not same, and some passengers require who are a little bit weak in constitutions may require may not be able to cope up with the lack of oxygen at even lower altitudes such as 12, 13,000 feet, and some healthy, very healthy individuals are able to cope up with the oxygen lack of oxygen which is very small, up to 15,000 feet. Therefore, the provisions are given. And I just want to explain once again, with this provisions only mean as long as the aircraft is above 15,000 feet, the entire set of passengers have to be supplied with oxygen. That's what that is, at least for a minimum period of 10 minutes. This 100% passenger should be supplied, which means that the aircraft descent profile should be planned in such a way that you should be able to descend below these altitudes within the time frame which is limited by the oxygen system supply. That is, of course, dependent on the pressure, and as we already discussed, the type of the system requires a fitted chemical or gaseous system, and other provisions, number of passengers, etc., etc. So this is how these are all reflected in the performance manuals of the aircraft, and they are not very complicated. They are fairly simple to understand once uh, working is reflected in the operations manual once you go through that. In addition, there are handheld oxygen cylinders which can be supplied in case of extreme emergency and extreme cases of patients and things like that. Let's discuss a specific case of an aircraft fitted with chemical oxygen generators, and let's see the pressurization failure profile of such an aircraft. Here I have given an example. Um, Here you can see the x-axis is in terms of minutes and the y-axis in terms of flight level altitudes. So depending on the chemical generator, this is a system limitation, and the aircraft has to follow this profile to meet the legal requirements of oxygen requirements. That means in this diagram, if you stayed at flight level 290 above more than the time specified, then you may not be able to meet the oxygen requirement we just discussed. So let me explain this. Now here, within the first 7 minutes of decompression taking place, the aircraft should be less than flight level 290, and by 21 minutes of time the aircraft should be below flight level 140. It is then that these aircraft will be able to meet the legal requirement. Having seen the oxygen descent profile depending on the oxygen fitted, now here I have tried to show the aircraft descent profile that is possible, demonstrated and possible. So this aircraft profile obviously should meet the chemical for this particular system in this diagram, the chemical generator oxygen system, its profile. That means the aircraft profile should always be slightly be lower conservative than the oxygen profile which has been given by the manufacturer. So of course this aircraft profile has to clear the obstacles by 2000 feet, above 10,000 feet. That's what we saw the Enroute requirement is. So let's see this diagram once again. On the x-axis now I have shown the distance to be flown. That means by the 6th minute, by 6 minutes, the aircraft would fly up to 28 nautical miles, and by 21 minutes the aircraft would travel about 170 miles, and as shown in the next it will travel 380 miles. This is how we have determined the aircraft profile. Now this has to be compared as against the obstacles on a particular route, and the operator has to satisfy the regulator that it meets the obstacle clearance limits, and then the route operation shall be approved by the regulator. So, of course, these are all well documented, and the routes are all well studied. So, there is a separate planning section which will do this job for people in the for operations in airline. So, however, we need to be aware of all these provisions. Now, what about multiple failures? The operator would satisfy that your route and your aircraft profiles are coherent, and it satisfy the legal requirements in case of an engine failure. And he will also perform and demonstrate the calculations and satisfy that it meets the pressurization failure requirements. Now, thankfully, the engine failure and pressurization failure simultaneously has happening cannot be are not being considered. Let us understand, in case of a pressurization failure, both the engines are available. So, uh, net flight path and maintaining an altitude, safe altitude, and gaining height in case of a requirement, and etc., are not very critical as in case of a one engine failure scenario. So there is nothing, there are no concept of a net flight path, and which is not required since both engines are operating. And of course, as I told you, obstacle clearance is not a big challenge. Now, uh, uh, when a rapid decompression takes place in an aircraft, the idea is to descend to a lower altitude as soon as possible. The operations manual is going to list out the actions, and it is going to uh, uh, enumerate actions in such a way that the aircraft will increase speed up to VMO MMO, and uh, lower the speed brakes so as to carry out achieve a maximum rate of descent. So, in in case of a pressurization failure scenario, that is what is being assumed, and that is what is the provision to be catered for in case of an eventuality. But it is possible there is sometime pressurization has failed due to structural failure or damage to a structure, in which case you cannot increase speed to VMO, MMO, and therefore consequently your rate of descent achieved will be much lesser. Thankfully, at the moment, legal requirements have not specified any great provisions for such a failure, because such an eventuality of a structural failure when the aircraft is flying at high altitude is extremely low. So, at the moment, the legal requirements specify the requirements where the aircraft is assumed to be able to increase the descent speed to maximum VMO and MMO, and use of speed brakes is permitted, and then aircraft continues to descend, achieving fairly high rate of descents. Here we come to the end of the lesson, and I can assure you, as you start flying and go over the provisions of aircraft performance Enroute, you will find the subject very interesting. And the more you understand, it gets more and more interesting, and uh, it enables you to study the subject in much greater depth. So this is about Enroute performance, and there are much more nuances. I've just covered the legal and the salient aspects of Enroute performance. I'm sure you found the lesson very interesting, and as usual, please feel free to pass your critical comments by means of email in the email given below. And I thank you all for going through the lesson. And I intend taking one more on the landing perform, one or two more, I'm not sure, on the landing performance, which again I will encourage you to follow them. And there are several other lessons which are going to be beneficial in my YouTube channel and my website as well. So I encourage you all to go through and pass on this information to as many people as possible, so that maximum would benefit out of these lessons. I thank you all for patiently going through this lesson.